And here we are again on this lovely day, and I'm sure that you're energized and enthusiastic about your mathematics. We're going to be taking a look at graphs of the derivative function. So if I've got y equaling this function here, it's shown in that heavy black. We can produce the derivative function on a graph based on just looking at this sketch. Key things to look for. To begin with, look at the turning points. So here's the first turning point on the original graph. Notice that if we drew a tangent line at that point, we would get a flat horizontal straight line with a gradient of 0. So the slope of the original curve at this particular point is 0. Therefore, its derivative should be 0 for that same value of x. And there it is shown. Another turning point. Again, the slope of the original curve is 0, so therefore its derivative should be 0 at that same value of x. And finally, the third turning point, and there it is again. So we have our intercepts for the derivative function here, here, and here. They correspond to the turning points on the original graph for the same values of x. We now take a look at the shape of the original graph, where the graph has a negative gradient, positive gradient, negative gradient, positive gradient. And that will help us fill in the gaps. So here we can see that the original function is going down towards the right, so it has a negative gradient. So therefore its derivative should be values less than the x-axis, which they are. Here the graph is increasing, has a positive gradient. So between here and here, between those values of x, then the derivative should be positive, which it is. Here the original graph goes down towards the right, so it has a negative gradient, and you can see that the derivative is negative. From this point onwards, the graph goes up towards the right, therefore the derivative should be above the x-axis, it should be positive. So that's making sense. Another key thing to point out is the turning points for the derivative. So let's look at this derivative here, and we have a minimum turning point. This is the lowest that the slope will reach for this section of the graph. And this makes sense because if you take a look at the corresponding x value and where it relates to on the original graph, you can see it's here. And at this position, the original graph is at its most steepest, and it's going in the negative direction. So it makes sense that its derivative, the original graph's derivative, would produce a minimum turning point. Same approach over here on the left. Here's the derivative, it's a maximum for this derivative function, and for that same value of x, then you can see that we are at its absolute steepest, just there on the original dark line. And of course, that same value of x, it corresponds to a maximum turning point for the derivative. So that's what we're looking at there. Firstly, just look at the turning points. They will represent the intercepts of the derivative function. Then take a look at the basic shape of the original graph and where it's going down towards the right, where it's going up towards the right, and they'll give you a picture of whether or not the derivative should be above the x-axis or below the x-axis, i.e. positive or negative. And then finally, the turning points of the derivative function correspond to the steepest sections of the original graph. So just to summarize what I've been speaking about, we've got the graph of y. These are the key things to take a look at. Positive gradient, negative gradient, stationary points. So the stationary points, the turning points for the original graph, the same x value will be the x-intercepts for the derivative function, the y dx. Where the original graph goes down towards the right, that is, it has a negative gradient, then the derivative function will be below the x-axis. For where we have a positive gradient, the graph goes up towards the right on the original function. The derivative function will be sketched below the x-axis. Here we've just got a reminder about the original graph and then what its derivative would look like. So a straight line, y equals mx plus c. If we take the derivative of that, we'll get y equaling m, and that will be a horizontal straight line that runs parallel with the x-axis. It'll have no gradient itself. A quadratic will become a linear, and a cubic will become a quadratic. It's also important to remember the rules of differentiability. So in order for a function to be differentiable at x equaling a, then the following conditions must be met. Firstly, it must be continuous. So you need to be able to sketch the entire graph without taking your pen off the paper. And if we're looking at trying to find the derivative at a particular point for x equaling a, then there must be no break or hole there. That's the idea of being continuous at x equaling a. Secondly, we must be able to draw a tangent line at that point x equaling a. So that means that there's no endpoints. So if we've got a certain region or a certain domain for the graph, and we're trying to work out the derivative, at the endpoints we will not be able to work out the derivative. And there must be no sharp corners. So sometimes when there's a hybrid function, you'll see that there's a point there where the two rules meet, and that will form a sharp cusp. And in those situations, you will not be able to work out the derivative because you don't know really where to draw the tangent line. In problem 1 here, I've got a function h of x, and it's sketched below. And I need to work out where the derivative is greater than 0, where it's less than 0, and where it's equal to 0. So for a, where is the derivative greater than 0? So if we look at our graph here, I start from negative infinity, I go all the way up to negative 3. Notice that I'm not including negative 3, because at negative 3, the derivative is a turning point where the gradient is in fact equal to 0. So I'm looking at just values which are greater than 0. So to begin with, I start from negative infinity and I go up to negative 3. I'm not including negative infinity and I'm not including negative 3. The second section of the graph where the gradient is positive, so going up towards the right, is here. So I start from a half and I go to 4. Again, I'm not including the turning points. So it's from a half to 4. Circular brackets are used to show that I'm not including the half and I'm not including the 4. So these two different sections are in union. So I use the union symbol here. So it's negative infinity to negative 3 in union with a half to 4. Whereas the graph negative, so the first section where it's negative is from here to here. So I'm looking at negative 3 to a half, and again, circular brackets. The second section is from 4 to positive infinity, and again, I'm using circular brackets. Once more, we want to have both of these, so we use the union symbol to show that it's the two. And for C, where is the derivative equal to 0? It's going to be equal to 0 at the turning points. So I'm going to have x equaling negative 3, x equaling a half, and x equaling 4. So I should obviously have x equaling a half listed in there as well. G'day there to all my brilliant mathematicians listening in intently to this fantastic video. Here we're going to be taking a look at problem 2. We're required to take a look at the original graph and sketch over the top of it the derivative function. Remember, you're looking for turning points, you're looking for where the original graph has a negative gradient and also a positive gradient, and you're also considering taking the derivative of the original function and what that basic shape should look like for the derivative. So to begin with, for A, we have a parabola. So if we know we take the derivative of that, we should get a straight line graph. The turning point corresponds to the derivative having an x-intercept for that same value of x. On the left-hand side of the turning point, we have a negative gradient, so therefore the derivative function should be shown as negative values. On the right-hand side, the original graph goes up towards the right, so therefore it has a positive gradient, and again, the derivative function should be shown as being above the x-axis, that is, that it's positive. In B, we have a straight line graph in the format y equaling mx plus c. If we take the derivative of that, we'll get a constant, and if we show that constant, then that is a straight line that is parallel with the x-axis with no gradient itself. I have two positions given to me on the original graph, -1, 0 and 0, 1. If I calculate the gradient of this red line using rise on run, I'll get a gradient of 1. So therefore, I can draw in a horizontal line y equaling 1 to represent the gradient of this original function. In C, we have a cubic kind of shape. So I need to go straight to the turning points. So here's a turning point, and that should correspond to the derivative function having an x-intercept. Drawn a little bit wonky, but that's where it should be. And the same thing over here, got a turning point, therefore for that same x value, the derivative should have an x-intercept, which it does. On the left-hand side here, it's going up towards the right, therefore above the intercept we should have that shown, being a positive gradient. From here to here, the original graph goes down towards the right, so therefore the corresponding x values for the derivative function are all below the x-axis. And from here, the graph is positive going up towards the right, so therefore the derivative function is shown as being above the x-axis. D, we have an inverted parabola. And so if we take the derivative of a parabola, then we should get a straight line graph. So that's our basic shape. Turning point on the derivative function is going to correspond to an x-intercept. On the left-hand side of the turning point, the graph is going up towards the right. So it's increasing, has a positive gradient. So therefore the derivative function needs to be shown as being above the x-axis. On the right-hand side, the original function goes down towards the right. Therefore, on the derivative function, we need to show that as having a negative gradient. Here we have another straight line graph in the format y equaling mx plus c. This time, if we calculate its gradient, we'll get -1. So again, the derivative function is shown as y equaling -1, a horizontal straight line parallel with the x-axis. For F, another cubic example, turning point, so therefore the derivative for that same value of x will have an x-intercept. Turning point, x-intercept on the derivative function. Between here and here, the original function is increasing, so it has a positive gradient. So we've got ourselves all the values being above x for the derivative. And here we've got a negative section, and there we've got a negative section, so the derivative function is shown as being negative. Also notice that if we take the derivative of a cubic, we're going to get a parabolic shape, and that's what we see there in green for the derivative. And finally G. G, we've got a horizontal straight line at y equaling 3. If we take the derivative of a constant, then we'll get 0. So therefore, the derivative of this red line will become this green line, y equaling 0. Okay, everybody, welcome to this fantastic problem. It's as hard as it gets. And if you can get your head around this, you're in a really good space, and you obviously thoroughly understand the ideas about taking an original function and sketching its derivative. To do this, I'm going to start with looking at the turning points on the original graph. So here's my first turning point I'm considering. So the derivative function will have an x-intercept for that same value of x. Another turning point, x-intercept for the derivative. Notice on the right-hand side of this turning point, the graph goes down towards the right. It has a negative gradient. So the derivative function will be shown as being less than 0, which it is here. Between this turning point and that turning point, the original graph is increasing. That is that it has a positive gradient. So between those x values, the derivative function needs to be shown as being above the x-axis. That is that it's positive. Notice that I come up with this idea of a maximum gradient here. So the derivative is at its maximum for this value here for x, and that corresponds on the original graph to this position, and there you can see that the original graph is at its most steepest. Right, we've got it coming down to a 0 gradient, it's increasing, it's becoming steeper, there it is at its most steepest. Now it's starting to become flatter and flatter and flatter, it's getting to a 0 there. So a maximum in the derivative corresponds to the steepest part of the original graph. In this section here, you can see that the original graph is decreasing and has a negative gradient, and therefore the derivative function is shown as being below 0. That is that it's negative. Let's consider this straight line. I know that taking the derivative of that will give me a horizontal straight line that is parallel with the x-axis. I'm going to use the point -4, 9, and I'm going to use the point that should be listed as -2, 14. If I take the gradient of that using rise on run, I'll get positive 2.5. It makes sense because the graph goes up towards the right. And here I'm showing that, going on indefinitely in that direction. But why do I have a hole? The hole is at x equaling -2. That corresponds to this cusp here. And with a cusp, I cannot differentiate at that point. And the reason for that is that I'm unable to draw a tangent line at that cusp. I can draw a tangent line on a straight line. I can draw a tangent line at any point on the curve. But here, I would be unable to draw a tangent line. Therefore, I'm unable to calculate its derivative. And it's not differentiable. Therefore, if I sketch a derivative function, it will have a hole at that position. Rockets. I love rockets. Do you love rockets? Problem 4 is all about rockets. A rocket is launched from Cape York Peninsula so that after t seconds, its height, h of t, is given by the function ht equals 20t squared, where t is between 0 and 150 seconds, i.e. after 2.5 minutes. Well, as soon as we get one of these kind of questions, what we should do straight away is define it in our CAS calculator. So menu, actions, define. And I want h. Now I'm not going to use the variable t, I'm going to use x. And this will ensure that I'll be able to graph it if I need to. So h of x is equal to 20 times x to the power of 2. And it's given that x is going to be greater than, greater than or equal to 0, but less than or equal to 150. All right, so I define my function. In A, we need to find the height and also the speed for t equaling 120 seconds. So to calculate the height, I just substitute t equaling 120 into the h of t function. So I want h of 120. And there it is, 288,000 meters. That's its height. Now, if we consider the second part of the question, we're after the speed. Now the speed is distance over time. We've got this height function, so think of that as being the distance versus time. So clearly, if we're after the speed, it's simply the derivative of this function. So I can do this in two ways. I can work out the derivative of the height function and then substitute 120 into it. Let's look at that scenario. We can work out the derivative easily on our CAS calculator. Menu, calculus, derivative. And it's going to be change in h of x with respect to x. So in here I'm going to put in dx. And now it's h of x. And this will give us a rule. So you can see that the rule for the derivative is 40x, where x is between 0 and 150. So a way of me calculating the speed at 120 seconds would be to simply say, let's have 40 times 120. And you can see I can get my 4,800. There it is there. Now, alternate approach, and this is the approach I'd like you to use, is to say menu, calculus, derivative, and it's of h of x, and now put the condition in that x is equal to 120. What will happen here is that the CAS calculator will work out the derivative of h of x, and then after it has that rule, it will substitute x equaling 120 into it to get that 4,800. Some of you would be thinking, well, why don't you just, instead of putting x in, put in 120? Let's see what this produces. Menu, calculus, derivative. And we want h of 120. And it's 0. Now what's happening here is that the calculator is evaluating what h of 120 is. So it's substituting 120 in to the h of x function. And when it does that, as you saw earlier, it gets that really large number, 288,000. And then after that's been achieved, that constant, it then takes a derivative of that. And of course, if you take the derivative of a constant, the answer is 0. So when you're using your CAS calculator to work out derivatives, put it in this approach here. There's your rule, you're working out the derivative of the rule, and then after you have the derivative rule, you substitute in a value for x. That's the approach that you should use. So in part B, we need to work out how long it takes for the speed to reach 1,000 meters per second. So we're going to use our CAS calculator. So menu, algebra, and solve. And now we're going to bring in the derivative function. So menu, calculus, derivative, respect to x. And inside here, we're going to put in the h of x function. So we've got, at the moment, we've got solve, and then inside that, we're working out the derivative of h of x, and we want the derivative of h of x to equal 1,000. I'm going to solve for x. I'm going to go comma x. And you can see we get x equaling 25, meaning 25 seconds. And that's all I need to work out here. Just state that there. h of t, which is the derivative, make it equal to 1,000, and then if that's the case, t will equal 25 seconds. Please notice I'm using my CAS calculator, and all I need to do is show the stuff in red. Okay, I've stated what h of t is. For part A, I've got h of 120 equals this amount here, so that's my height. and I make it clear by writing height equals that. When we're talking about the speed at 120 seconds, then I understand that it's the h prime of t function, the derivative function that is used, and that t equals 120, and I get that amount there. Here's my speed. And then I've explained B already. I want the derivative to equal 1,000, and when that's the case, t must equal 25 seconds. That's my answer. The stuff in green here are just the steps that I've already shown you through the screencast. In problem 5, we're going to be involving a lot of algebra. Let's look at the first part. A. Find the equation of the tangent to the curve y equaling 2x squared take away 2 at x equaling 2a. Now if we just had x equaling 3, this would be a very routine type of question, but it's not. We have an unknown constant a, and we're interested in the tangent line for where x equals 2 lots of that unknown constant. Our approach is going to be exactly the same, but we're going to have a lot more steps involving algebra and this unknown a value. So you can imagine this shape here, y equaling 2x squared take away 2. This is just a parabola. We're talking about the tangent line. So the fundamental idea here is that if we can calculate the gradient of the curve at x equaling 2a, that will give us the gradient of this tangent line. If I substitute 2a into this y rule, then I'll have the y value for where the tangent line is at x equaling 2a. So I'll have a position, a certain position, and so given that for the tangent line, I'll have a point that is on that tangent line, and I'll also have the gradient of that tangent line. I'll be able to come up with an equation for the tangent line, and of course, that equation will be in terms of a. So we begin. Here's f of x. I take its derivative. Now, what I'm going to do is substitute 2a into f of x, and I get 8a squared minus 2. So now I know that 2a, comma, 8a squared minus 2 is a point that is on the curve, and that point is, of course, also on the tangent line. I now substitute x equaling 2a into the derivative, and I get a gradient of 8a. So I know the slope of the tangent line is also equal to 8a. Let's go now and work out the tangent line. The tangent line is a straight line, so it's in the format y equals mx plus c. The gradient is 8a. A known point that is on that tangent line is 2a, comma, 8a squared minus 2. So I set y as equaling 8a squared take away 2. I set x as equaling 2a. And I can solve for c, the unknown constant at the end for this equation. So I end up with y equaling 8a multiplied by the variable x minus 8a squared take away 2. That's the equation of the tangent line. B. Hence find the x-intercept of the tangent line in terms of a. So of course, for our x-intercept, y is equal to 0. So I set y equaling to 0, and I solve for x. So obviously I missed a few steps there, but basically you would add 8a squared and add 2 to both sides, then divide everything by 8a, and that will simplify to being this expression here. So x is equal to that. C. A straight line with the equation y equaling 2x minus 2 passes through the x-intercept of the tangent line. Find the value of a. So this line here passes through the known x-intercept. So Obviously, if that does go through an x-intercept, the value of y is 0. So I set it as equaling 0. Solving for x, I get 1. So I now know the value of x for that x-intercept is x equaling 1. I make that equal to my right-hand side. On the left-hand side, I have the x-intercept in terms of a. And if I solve for a, I get a equaling a half. So I now know that unknown constant a is in fact a half. So there's the value of a. D, what is the equation of the tangent line? Here's my tangent line in terms of a. I've now substituted the found a value, and I now know that the equation of the tangent line is in fact 4x minus 4.